In this video, we're going to look back to the previous module where we talked about linear growth versus, in this module, exponential growth. I want to focus your attention to the explicit form of each, although there is a recursive form of each. So in linear growth, we started with some value, which we're calling p sub 0 or p naught. And each time we're adding in the same value, we're adding in some common difference d times the number of years. Whereas in exponential growth, we started with p naught or p sub 0, and we're multiplying by this growth multiplier 1 plus r, where r is our growth rate for some number of years. So let's just take a look and see at the difference between how we would work a problem using both growth models. Okay, in this problem, in 2005, there were 5,500 inhabitants in a certain city. Okay, that seems to be where we're starting the problem. So we'll say p naught equals 5,500. It is important to keep in mind, though, that when we say p naught, we're referring to the year 2005, right? That's key. Predict the population in the city in the year 2025. So we're thinking about if 2005 is our p naught, sometime later, right? We're in the year 2025. In fact, that's 20 years later. We will call that p sub 20, right? In other words, we're going to be concerned with n equals 20. All right, so let's take a look at the two different things that we want to talk about here. So A, the growth rate is 500 people per year. That means we're always going up by 500 people. That definitely would be linear, right? We're increasing by the same amount every time. We're going to use this explicit form. So we say, oh, okay, so then our population for any year is equal to p naught, which is given as 5,500, plus, looking up at the formula, dn, where d is our common difference. In this case, the common difference is given here as 500. So we're going to say plus 500 people every year. Okay, so we're supposed to use this model to predict the population in the year 2025. So we're going to be plugging in n equals 20. All right, so p sub 20 is 20 years later, 5,500 plus 500 people per year for 20 years. All right, we're going to grab a calculator and type this in. 5,500 plus 500 times 20. I have 15,500 people. Okay, so that's where the population would be. Let's take a look at B, the growth rate. Oh, the growth rate. That's how much we're going up each year. So that means year to year, we're going to be getting 2% more per year. This is exponential growth. All right, so we're going to be using the formula to the right. We're going to be using p sub n equals p naught times 1 plus r to the n. Now, don't forget that if r is 2%, right, that means 2 out of 100. We can convert that always to a decimal by taking 2, in this case 2, or the number dividing by 100, we'll get 0.02. So when we plug into our formula, we're going to get p sub n equals p naught, 5,500, times 1 plus r. Okay, let's go and do that in our head. If r is 0.02, we're going to get 1.02 to the nth power. Now, let's go ahead and find p sub 20, right, by plugging in 20 for n. So definitely need a scientific calculator here. All right, so we have 5,500 times 1.02 raised to the 20th power. And this is 8,173 people. So in this particular problem, what we find out is that the growth rate, linear, if we just add 500 people per year, we get more people than if we just add 2% per year. But what would happen over time? Let's take a look graphically. I'll use Desmos to further explore this. Okay, here we are on Desmos. You can see on the y-axis, I have population. On the x-axis, I have years. It's not an expectation that you learn how to use this. This, again, is at desmos.com /calculator. I'm going to type in my linear model first here so you can take a look at what goes on. So our linear model was p sub n. I'm just going to use p. The population is 5,500 plus 500 people per year. And it looks like that. Now, this is a graph of our population over time. We've already took a look at p sub 20, right, way out here. We know that there's 15,500 people at that point. Let's take a look at the exponential model as well, which is 5,500 people times our growth multiplier 1.02 raised to the n power for any number of years. And we also knew that, yeah, way out here at 20 years, there's 8,173 people. And so you can see that the red line, which is the linear, is above the exponential line. But I want to zoom out and show you what would happen over time. Over time, the linear model would seemingly stay at this, well, it stays at this constant rate, but this exponential model eventually begins to pick up speed. And over here at some point, and actually Desmos is given this after 128 years, they would be equal to each other, and then the exponential would always pass. Now, what happens is no matter what this growth rate is, as long as it's above 1, that will always happen. It will happen faster if the growth rate is larger. For example, if it wasn't 2%, let's say it was 5%, you would see that right away within the first 20 some years, it would pass it. If it's a 12% growth rate, it just really quickly is going to pass it. So you can see that these, well, let's go down. What if it was smaller? What if it wasn't 2%? What if it was 1%? Well, it just looks so much bigger. But if you just keep zooming out, and you have to zoom out a long ways, you can see it eventually it passes it. These exponential growth rates always form this curve. So eventually they'll always pass a linear growth model. So this is kind of how you compare the two. And I hope you've learned something more about comparing the two with this video.